This is a new topic. So in this lecture, let us discuss the digital filter structures. As I talked about earlier, digital filters require only three basic blocks. Okay, so one is the delay. It is denoted by C inverse. So you put a small box and Z inverse. This is input and this is output. And the second one is scalar multiplication. Okay, so you put a small circle and within the circle you put the multiplier which you want to multiply. And the third one is addition or subtraction. So this is denoted by, you put a summer here and this is plus and this is plus for addition. In case if you want to do subtraction, then you put like this, minus and plus. And this one is for addition. Okay. And in order to respect the actual hardware process of addition or subtraction, we don't use more than two signals at any adder. For example, you cannot put like this three signals in an adder, because if you take a actual hardware, it can't add more than two numbers at a time. In case if you want to add 5 plus 3 plus 2, the hardware first adds these two values and stores the result, and then again adds 2 and then finally gives you 10. Therefore, you take any hardware, it cannot handle more than two numbers. That is why we must respect the process which occurs in the hardware. So we are not supposed to use like this. Okay. Now if you are given a structure, you can always analyze it and you can find the transfer function. Okay, so digital structure is given. Digital structure is given. You can analyze the structure and you can find the transfer function. So this is always possible. But the problem here is, given the transfer function, and the question is, how do you find the structure? Okay, that is the question. Here, given the structure, you can always analyze and you can always find the transfer function, no problem at all. But given the transfer function, how do you find the structure? In case if you can find one, is this unique? The transfer function is given and one guy, he came up a structure, and you can ask a question, is this unique? And this is called a synthesis problem. So synthesis problems are always characterized by the fact that if one solution exists, this is a very, very important statement. If one solution exists, then there exists an indefinite number of solutions. There will exist infinite number of solutions. But a solution may or may not exist to a synthesis problem. Okay. On the other hand, analysis problem solution, however complicated, will exist. Okay. So synthesis problem doesn't mean that always the solution exists. The solution may or may not exist. But if one solution exists, then there will exist an indefinite number of solutions. But on the other hand, analysis problem solution, however complicated, will exist. Now we will illustrate by two examples of analysis, and then we will go to synthesis. Okay, so if you are given a structure like this, let me draw it. Okay, in the process I will also point out some of the disciplines that we have to observe. So x of n, then p0, okay, and then there is a delay z inverse, and then you have a multiplier p1 that adds to summation, and then this adds up to another summer. Okay, this is my y of n. Okay, there is a delay here, and there is a multiplier minus d1, and then adds here. Okay, so this multiplier is minus d1, minus d1. Okay, you must show the direction of signal flow. If an arrow is missing, your structure does not make any sense. Okay, suppose the problem is that of analyzing the structure. Well, it is rather easy. You can say that y of n is equal to, this y of n gets two signals, this point and this point A and B. At point A, I am getting again two signals, and this one and this one, x and y, or I can write C and D. At point C, I am getting P0 times x of n, and at point D, I am getting P1 times delayed version of x of n, so x of n minus 1, P1 times, and these two guys are added. That is why I put this plus sign. The plus sign is coming because of this adder. This plus sign is coming because of that adder, and this n minus 1 is coming because of this delay, and this P1 is coming because of this scalar multiplier. Okay, so this is what I will get at the point A, and then at point B, this yn is delayed by one sample. So in this point, y of n minus 1 delayed, and this y of n minus 1 is multiplied by minus d1, therefore minus d1 times y of n minus 1. So it is a recursive structure because it requires a feedback y of n minus 1, the previous output, and therefore I get y of n plus d1 y of n minus 1 is equal to p0 xn plus p1 xn minus 1. And all that I have to do is now take the z transform of both sides, and the result is y of z plus d1 z inverse y of z is equal to P0 x of z plus P1 z inverse x of z. Y of z you take commonly outside, 1 plus d1 z inverse is equal to x of z P0 plus P1 z inverse. So y of z divided by x of z is equal to P0 plus P1 z inverse divided by 1 plus d1 z inverse. That's it. So this is the transfer function. Okay, let me call this as h of z. Now this is the first order transfer function, but here I need two delays. Obviously the structure that was asked to be analyzed is not canonic in delays. Why? For first order filter means I should use only one delay, but I used two delays here. See, z inverse, one delay, and here one delay, two delays. So this is not canonic in structure. The structure which was given to us is not in canonic. This is a fact. See, this is a first order filter, right? And therefore it should require only one delay. It should not require more than one delay. But it is canonic in multipliers. We have three coefficients, P0, P1 and D1. Therefore we need three multipliers. So yes, we have three multipliers here. See, 1, 2 and 3. Three multipliers. Therefore the given structure is not canonic in delays, but it is canonic in multipliers. So I should note down this point. Okay, so the structure that we analyze is not canonic in delays, but canonic in multipliers. And later on we will show how to obtain a canonic structure and canonic structure in both the multipliers as well as the delays. But before that, let us take another example. And this structure is fairly involved structure. So we have capital X of z, and this capital X of z adds to, draw the structure. Okay, let me put two adders. So okay, and here we have z inverse and a feedback here. Feedback here with a multiplier k2 plus like this. The other signal comes from the multiplier k1, and it goes here, and there is a z inverse here, and let me put one more summer, and the structure is a little complicated like this. There is this summer, and for this summer another one is, let's say this is minus k2 like this. You put a arrow mark, Okay, this summer gets an input from this point. Okay, and then from this point you put alpha 2, another multiplier, and then you put a summer, and the summer gets one more output, one more input via this multiplier alpha 1, and then like this. So from this point, from here multiplier alpha 1, and from here multiplier I have a multiplier alpha 2, and this is the output y of n, or I can write y of z. Okay, you must show the arrows. Okay, you must show the arrows. I mean, you must show the signal flow. Even if it is redundant, even if it is obvious. You see, if I have not put the arrow here, then because I have indicated the output, okay, the input is obvious. Suppose if you put the arrow mark like this, and even if you don't put the arrow here, it is obvious. Even if you don't put the arrow in the input, but it is advisable that you must show the arrows. Okay, without arrows, don't leave any link. So it is a fairly involved structure. All that I have to do is to find out what are signals. Okay, what are the signals in this? In this point and in this point, in terms of x of z. Okay, I need to find out y of z, so that if I know the signal value at this point, let me call a and this point b. If I know the value of the signal at point a and point b, then I will be able to write down the output very comfortably. So it is a good idea, except at trivial nodes, to indicate some intermediate signals. Okay, so we indicate this point as w of z. There are many other ways of doing it, but I did it like this. And then this point, signal flow, I will call v of z. Okay, that's enough. I don't have to indicate any other, because all other signals can be expressed in terms of this w of z and v of z in this point. If I know in this point, then I will be able to know the point at b. I will be able to know the signal at point b. Similarly, if I know w of z, then I can tell you what is the signal at point a. So we need to first write down w of z and v of z, and from that w of z and v of z, we will be able to write down the y of z. Okay, once you know w of z and v of z, then you can express the output in terms of w of z and v of z. And you notice that we can write w of z as equal to, see, the x of z is coming here directly, so x of z, and then and this guy is coming over there, minus k1 times this v of z is coming over, so minus k1. Why minus k1? Sorry, this is minus, I forgot, minus k1, this multiplier is minus k1. The input to this scalar multiplier is v of z delayed by 1, so z to the minus 1 v of z. And then one more signal is coming, k2, and this guy is coming over there, so k2, and the input to this multiplier k2 is w of z but delayed by this one, so z inverse w of z. Okay, you just look at the figure, then you'll be able to understand how I wrote this. Let me delete this all, guys. See, this point is w of z. In this summer I have two signals, let's say 1 and 2, or let me write small a and small b here, and again small a is the output of this summer and small a is the summation of these two signals. Let me call this is c and d. Therefore a is equal to c plus d. What is c? C is x of z, plus what is d? D is nothing but the output of the multiplier, scalar multiplier, minus k1. What is the input to the scalar multiplier? This v of z. V of z is delayed by z to the minus 1 and multiplied by minus k1. Therefore minus k1 delayed by one sample and then v of z. That's what I wrote here. So this point corresponds to d and this is c and this one is b. Okay, so that's how I wrote w of z. And I think v of z is pretty easy to write. V of z, again 2 points. Let me use, this is 1 and this is 2. So what is 1? 1 is, there is a scalar multiplier, minus k2 times w of z, right? Then w of z is delayed by this delay, so z inverse w of z. So therefore minus k2 w of z plus z inverse w of z, that is minus k2 plus z inverse multiplied by w of z. This is v of z. Let me call this is equation number 1 and equation 2. Now you can eliminate one variable from these two equations. Now what is y of z? See, y of z contains again two parallel paths. Let's say this point is S and this point is P. At point P, P is the output of multiplier alpha 2. What is the input to the multiplier? W of z delayed by one sample. So therefore at point P, alpha 2 multiplied by one delay and then w of z. What about at point S? The v of z is coming like this. So it is multiplied by alpha 1 at point S and then delayed by one sample and then v of z. So I have alpha 1 times z inverse v of z plus alpha 2 z inverse w of z. Let's see equation number 3. So you have three unknowns, y of z, v of z and w of z, and v and w already related through these two equations 1 and 2. So all that you have to do now is to eliminate w. Whatever way you do the algebra, you can verify. Okay, and okay, let me do it, no problem. Substitute equation 2 in equation 1. So w of z is equal to x of z minus k1 z inverse v of z, you write it, okay, minus k2 plus z inverse w of z plus k2 z inverse w of z. Now x of z, then you take w of z commonly outside these two, therefore this is plus k1 k2 z inverse minus k1 z inverse plus k2 z inverse multiplied by w of z, and take this to the left hand side, then w of z 1 minus 1 plus k1 times k2 z inverse, right, plus k1 z to the minus 2. I did a mistake here somewhere else. k1 k2 z inverse, okay, k1 z to the minus 2, this is equal to x of z. Therefore w of z is equal to x of z 1 minus 1 plus k1 k2 z inverse plus k1 z to the minus 2. Let's say equation number 4, and substitute this equation in equation 2. What is equation 2? This one. So v of z is, what is v of z? V of minus k2 w of z plus z inverse w of z. You substitute here. Equation 2, this is minus k2 plus z inverse times w of z. So you substitute here, minus k2 plus z inverse times x of z whole divided by 1 minus k 1 minus 1 plus k1 k2 z inverse plus k1 z to the minus 2. This is v of z. Okay, let me call this is equation number 5, equation 4. Now you take equation 4 and 5, substitute in equation 3. 4 and 5, substitute in equation number 3, or your output equation. Therefore y of z is equal to alpha 2 times z inverse into x of z divided by 1 minus 1 plus k1 k2 z inverse plus k1 z to the minus 2 plus alpha, this is alpha 2 alpha 1 z to the minus 1 minus k2 plus z inverse times x of z divided by 1 minus 1 plus k1 k2 z inverse plus k1 z to the minus 2. So y of z divided by x of z, you bring x of z to the left hand side, this is equal to alpha 2 minus alpha 1 k2 times z inverse plus alpha 1 z to the minus 2 divided by 1 minus 1 plus k1 k2 z inverse plus k1 z to the minus 2. That's it. Okay, the job is done. So now this is the transfer function h of z. Now one can ask a question that is it always stable? Is it always stable? Not necessary, right? It is a second order filter. What were the conditions for stability? Stable if the k1 is less than 1, isn't it? Recall this condition. Okay, k1 is less than 1. The coefficient should be less than 1. I mean d1 is less than 1 plus d2. The general form is 1 plus d1 z inverse plus d2 z to the minus 2. It's a general form of a second order filter. If this filter has to be stable, then this d1 should be less than 1 plus d2. This is the condition that we derived in one of the earlier lecture. So compare this and that. What is d1 in this? d1 is equal to minus this coefficient. This is my d1. So d1 is equal to minus of 1 plus k1 times k2. And what is d2? This is d2. So substitute in this relation. Mod of d1 less than 1 plus d2 modulus. And d1 is 1 plus, if you take modulus, that minus sign will go. 1 plus k1 times k2, this must be less than, what is d2? d2 is k2, therefore 1 plus k2. Can you cancel in this anything? Cancel? No. You can't find out in the actual case. So what restrictions does it put? It says 1 plus k1 times k2, 1 plus k1 times k2 must be less than 1 plus k2 in order the filter to be stable. Okay, otherwise the filter is not stable. So this is the derived transfer function. So this transfer function is stable if and only if this condition is satisfied. d1 and 1 plus d2. What is d1? d1 is the coefficient of z inverse in the denominator. So this is z inverse. What is the coefficient? The coefficient is minus of 1 plus k1 times k2. What is d2? The d2 is the coefficient of z to the minus 2. So what is the coefficient here? k1. So that coefficient I have written here, 1 plus d2. d2 is the coefficient of z to the minus 2 in the denominator polynomial. Similarly, d1 is the coefficient of z to the 1 in the denominator polynomial. Okay. Now the other important thing in analysis and the synthesis of digital filter structures is the so-called delay free loop. So there should not be any loop which has no delay. And to illustrate this, I have taken another example. Okay, in some part of digital filter structure you get a flow diagram like this. So this is W of n, and then x of n, you put a summer, you get a feedback through D, and then you put another multiplier C. The arrows are very important. You put a summer here like this, and this is V of n, B, and A, like this. So Y of n. If you look at this loop, there is no delay. Okay, only you have 4 multipliers, A, B, C and D. There is no delay. So whatever xn comes, it gets multiplied by A instantaneously, then multiplied by B instantaneously, gets added to V, then multiplied by C, and then by D, again comes back, goes back. Okay, and it will either increase or decrease the signal, and this increment or decrement occurs instantaneously, and therefore in no time the signal either builds up to infinity or it goes down to 0, and such a loop cannot be implemented in practice. Such a loop, it does not make sense to implement this. You must have a delay. Therefore, delay free loops are unstable. You either get nothing from the output or you will get infinite output. Infinity, of course, you cannot get because your number of bits is limited, and therefore you will get a saturated arithmetic. So there must be a delay somewhere. Whenever you design your digital filters, and if by mistake such a delay free loop occurs in your realization, you can always avoid it by an equivalent structure. You draw the equivalent structure and then you can avoid it. So let me here, for example, you can write there are various ways of doing it. W of n is equal to W of n, where this point is equal to A times x of n plus C times D times A times V of n, right, plus B times C times D times B, C, D, again A times W of n. So this is equal to A, you can take commonly outside, x of n plus C, D, V of n plus B, C, D, W of n. I can write like this. Let me call this equation number 1. This is W of n. And then you can write the other equation, y of n you can write as y of n is equal to c times v of n plus bc times, look at the figure, b times c times b times c times w of n, w of n. And let me call this as equation number 2. From 1 we can write w of n minus a b c d, w of n is equal to a times x of n plus a c d times v of n. So w of n 1 minus a b c d is equal to a times x of n plus a c d times v of n. Therefore w of n is equal to a divided by 1 minus a b c d times x of n okay, plus cd p of n. I can write like this. So this is my w of n. Now if I want to construct this, then it looks as follows. X of n adds to cd vn, and then you have multiplied by a divided by 1 minus a b c d, and then this is w of n. Okay, multiplied by a by 1 minus a b c d, and you get w of n. Similarly you can find out y of n. So you have to find out w of n, then take b times this and add to v of n, and then multiply by c to get y of n. Okay, so you multiply by b, and then you put an adder, and then you put a multiplier c here, you get a y of n. So v of n input, that's it. Okay, this is v of n. In order to calculate y of n, I have to multiply w of n by b. Now you see this diagram. What is y of n? Y of n is I have written here, equation number 2, right? C times v of n, c times v of n plus bc times w of n. Okay, see this w of n is here, the w of n is multiplied by b and then c, so I got this one, no problem, no issues. And then c times v of n, I have v of n, and this v of n is multiplied by c. The only thing is I modified w of n. Now you see this, now you see in this diagram there is no loop. Okay, there is no delay free loop. You have broken the loop. So whenever a loop occurs due to a mistake on your part, or somebody has given you the structure like that, then you break the loop by writing the equations and making sure that these equations are implemented without recursion. And you see in this diagram there is no recursion here. Recursion means what? There is no feedback loop. There is no feedback loop without a delay. So delay free loops should be avoided. Delay free loops should be avoided. I want to make 2 points here. Okay, so the first point is, given a structure, we can always analyze. And we can find transfer function. Given a structure, we can always analyze and we can find the transfer function. The second point I would like to say is that the delay free loop should be avoided. In any structure, because they give, this delay free loop should give rise to instability. So therefore, at any cost, you should not allow a delay free loop in your structure, in your digital structure. Okay, now you consider the question of canonical delay structure. Okay, canonical delay structure and canonical multiplier. So in the very first example that we took was not in the canonic form in terms of delay, right? So what is h of z? H of z was p0 plus p1 z inverse. This is the first example, okay, that we took. If you go back, you can see this one. Okay, I'm going to write down this again. P0 plus P1 z inverse divided by 1 plus D1 z inverse. Let me write down here. Z inverse divided by 1 plus D1 z inverse. And this is delay non-canonic, but canonic in multipliers. Scalar multiplication or multipliers or whatever it is. Now in order to make it canonic, we represent this as h of z is y of z divided by x of z, which is p0 plus p1 z inverse divided by 1 plus d1 z inverse. Now I can write y of z as p0 plus p1 z inverse times x of z divided by 1 plus d1 z inverse. And now let me call this guy as w of z. Therefore y of z is equal to p0 plus p1 z inverse multiplied by w of z. So w of z is equal to x of z divided by 1 plus d1 z inverse. So w of z plus d1 z inverse w of z is equal to x of z. So w of z is equal to x of z minus d1 z inverse w of z. Okay, I have written it in a particular fashion. Okay, now x of z can obviously realized as follows: x of z, if the input output is w of z, then you delay w of z and multiply by minus d1 and add to it. This is plus and this is plus, and like this. Okay. Now to construct a y of z, all you have to do is, what is y of z in this? Y of z is p0 plus p1 z inverse multiplied by w of z, isn't it? Y of z is equal to p, what is that, p0 plus p1 z inverse times w of z. You expand this, p0 times w of z plus p1 z inverse w of z, isn't it? This is my y of z. So this figure you can simply extend. In this point I have w of z, but what I want for y of z is I should multiply w of z by p naught. So you put a multiplier here, p naught. This is my y of z, right? And one more thing is, you take w of z, delay by one sample. So this point nothing but z to the 1 z inverse times w of z, and this guy must be multiplied by a scalar multiplier p1. You put a p1 here, and then you put a summer here. Y of z, that's it. That's all. Now you see, I need only one delay here. There are 3 multipliers. So in the given transfer function, 3 multipliers, no problem. P0, P1, D1. So that's why we have 3 multipliers, 1, 2 and 3, no issues. But it is a first order filter, so I must use only one delay. So exactly we used only one delay here. Okay, so you have used only one delay. Therefore, this structure is delay as well as multiplier canonic. So you reduce the number of delay by 1. Okay, so I think this is a point that I stop. Thank you very much.